मधुर मनोहर अतीव सुंदर ये सर्व विद्या की राजधानी
Well, my dear students, now we are going to start 39th lecture in the series of mechanics of metal forming. In last lecture 38 we discussed two-dimensional cases wherein we also took the important focused points that one has to keep in mind while solving problem, starting with the mesh formation, starting with the solver option, starting with the selection of elements, starting with the order of elements, CST element, LST elements, and then we took an example and what kind of solution methodology has to be adopted as far as the stability is concerned, iterations, convergence issues we have already discussed. So far we have come to know the finite element method in a very correct manner, and we can now apply it for different situations in metal forming as well. So two-dimensional cases we have seen. In this lecture 39 we would see the three-dimensional elements, and let us see various three-dimensional elements that is available and that one can utilize it for finite element applications. So to start with, let us see the typical 3D solid elements. 3D element, it will be a solid element. So let us start with this figure where the typical 3D solid elements are shown. The first one, which is tetrahedron element, it is linear type. So linear, if the tetrahedron linear type has 4 nodes, you can see here, it is just like a prism. So the top vertex and the bottom triangle 3 elements, so that makes the linear tetrahedron 4 noded elements. On the other side, the corresponding quadrilateral linear tetrahedron element, when it is quadratic in nature. So now this element represents 10 nodes, and that is how it is quadratic in nature. The first one, when it is 4 noded, this tetrahedron is linear, and when it becomes 10 node, that means each edge, if you see, there is a intermediate center node is also created to make it quadratic. So that is the tetrahedron. Second type of 3D element that we come across is hexahedron, that we also call it as a brick element. So if you look at here, there is a linear brick element which has got minimum 8 nodes, that is the corner node. And on the other hand, if it is quadratic brick element, then that will have 20 nodes, you can see on the right side of that. So the 20 node, so 8 plus 12 node, because each phase we have created 4 the nodes at the edge, each edge rather 12 edges, 8 edges. So you have added 8 more, and that is how the total number of 20 nodes. So the linear hexahedron element, brick element is 8 noded, and the quadratic corresponding quadratic hexahedron brick element is 20 noded. Another kind of element that we come across, 3-dimensional solid element, we call it as a penta element. So penta element is shown here. So you have again 6 node here. You see, now the tetrahedron, if you shear it from the top, so that results into a penta element, and that has got 6 nodes. So if it is linear penta element, it is 6 noded. When it is corresponding quadratic penta, then it is 15 noded, as seen, one can see here. So in 3D case, in 3-dimensional, to solve the 3-dimensional problems, when one has to select 3-dimensional solid elements, one has to be very careful. So avoid using linear elements, that is 4 noded tetrahedral elements in 3D stress analysis. One has to be very careful if you are solving any stress analysis problem. So avoid using linear, that is 4 noded tetrahedron element, right, because it gives inaccurate results. However, it is okay for the static deformation or vibration analysis. So if it is 3D stress analysis, please do not use the 4 noded linear tetrahedron element. For other cases like static deformation and vibration analysis, one can use this as well. So with this basic 3 class of 3D solid element, one can now go ahead with the element formulation. So as you remember, we formulated the element for the 2D case. So here also one can, let us start the take case, the linear hexahedron element. So this figure shows one of the linear hexahedron element, where in 3-dimensional XYZ coordinate system. So these nodes are marked as 1, 2, 3, 4, 5, 6, 7, 8. So corresponding the mapping, if you establish the mapping from, and if one takes the local coordinate system or the natural coordinate system. So if you take the natural coordinate system, means from XYZ coordinates to zeta, eta and rho. So this mapping can be established in, this is shown here. So you have now zeta, eta and xi, rather it is called as xi. So xi and natural coordinate system. So the corresponding nodes, then it becomes as it has been shown there. For an example, node 1, this mapping becomes as -1, 1, -1, -1, -1. For the element 2, that becomes 1, -1, -1. For element 6, it is 1, -1, 1. For element 5, it is -1, -1, 1. For element 4, it is -1, 1, -1, and likewise this mapping is shown here. So once the mapping is established, and from XYZ to rho, zeta and xi, so the displacement field in the element can also be defined. Say if there is, because at now 3-dimensional, so each node is subjected to have 3 degree of freedom, and therefore 3 displacement would occur, and let us take it as u, v and w. So the displacement field element can be represented in terms of shape function ni's. That means u can be represented as over the summation I from 1 to 8, because now 8 elements. So ni ui, and v similarly I from 1 to 8 ni vi, and w from I is equal to 1 to 8 ni wi, and this is what has been shown here in this equation 1. This safe function in terms of the natural coordinate system, that is zeta, eta and xi, is shown here in equation number 12, that is equation number 2, that is n1, n2, n3 in terms of natural coordinate system it is shown. And for an example, n1 is 1 by 8, 1 minus zeta, 1 minus eta and 1 minus xi, and similarly all others are given in equation number 2, and n8 is 1 by 8, 1 minus zeta, 1 plus eta and 1 plus xi. So note that we have the following relation for the safe function, because the summation of the safe function has to be, that means ni must be equal to delta ij, where ij is equal to 1 to 8, 1, 2, 3, 8 etc. And this condition, it was valid even for 1D problem, it was valid even for 2D problem, we have seen. So what is the condition for the safe function relationship? That means summation over I is equal to 1 to 8, ni must be 1, that means n1 plus n2 plus n3 plus and so on n8, the all summation must be 1. And you remember, at the given element the value is 1 and odd other element is 0. So that is the way variation. So the coordinate transformation, that is mapping, as I told you, one can establish, and this mapping from xyz coordinate to natural coordinate system is given here. So in equation number 3, that means x is equal to I is equal to summation over I is equal to 1 to 8 ni xi. Similarly, y is equal to over the summation I is equal to 1 to 8 ni yi, and likewise for the z as well. So the same safe function are used as for the displacement field as well. So if one takes the isoparametric element, right? So if the isoparametric element is taken, so the Jacobian matrix can be calculated. So this Jacobian matrix has been shown here in equation number 4. So if you look at, that means Jacobian is the derivative of the displacement, that means deva u by deva deva psi, deva u by deva eta and deva u by deva xi. So this is what is called as the Jacobian matrix. So that, and then on the right hand side the Jacobian matrix J, capital J, and it is multiplied by the deva u by deva x, that is the transformation from xyz coordinate to natural coordinate system, eta, zeta, eta and xi. So that is what has been shown 14. That means if you want to calculate the vector of the corresponding vector of the displacement with respect to x, y and z, so that would be reverse, that is the J inverse multiplied by the right side of the equation number 4. So because deva u by deva zeta is equal to summation I is equal to 1 to 8 deva ni by deva eta ui etc., like one can. And similarly deva v by deva x, deva v by deva y and deva v by deva z, can be written as J inverse deva V by deva zeta, deva V by deva eta and deva V by deva xi. This is what has been written, this mapping in Jacobian matrix form in 5. And similarly for W as well one can write down. So the strain vector, so strain vector will consist of what? 6. So that is epsilon x, epsilon y, epsilon z, and the shear xy, shear yz and shear zx strains. So this is given here, that means epsilon x is equal to deva u by deva x, epsilon y is equal to deva v by deva y, and epsilon z is equal to deva w by deva z, and then shear component would be the summation of the two corresponding, right, and that is nothing but it is capital V d, where d is the nodal displacement vector, you all know as explained earlier also, and therefore the strain is can be written simply as capital B d as shown here in 6. That means the strain is a column vector of size 6 by 1, and capital B is your 6 by 24 size, and small d, that is the nodal displacement vector, it is of 24 by 1 size. So looking into this, the strain energy can also be calculated, right. So the strain energy can be calculated as capital U, where U is half of the integral over the domain sigma t epsilon dV, that is the strain energy, and that can be even further written as half of over the integral volume over the domain capital E epsilon transpose epsilon dV, and that is what is equal to half of integral over V epsilon t capital E epsilon dV, and that is what is equal to half of d capital transpose, and then the other factor, that is Bt E B dV, and outside this is d. So these are the all together. This equation has come earlier also, so I need not to discuss it again. So that is what is shown here in equation 7. So now the second thing is to find out the element stiffness matrix, is very important. So simply you remember same thing as earlier, the K as the elemental stiffness matrix can be calculated as over the integral on the given volume Bt capital E B dV. So K becomes what size? K, the stiffness matrix becomes 24 by 24. The B matrix becomes 24 by 6. E matrix becomes 6 by 6, and B transpose becomes 6 by B transpose becomes 24 by 6, and B becomes 6 by 24. So if you substitute all these in natural coordinate system, so dV can be written what, because from mapping from the xyz to zeta, eta and xi coordinate system, so dV will be written as determinant j, d zeta, d eta and d xi. So that is what is shown here in equation 9. So one can then find out the stiffness matrix. Now because the stiffness matrix here volume is now coming into picture, so that means there would be 3 integrals. That means integral, first integral -1 to 1, second -1 to 1 and third also -1 to 1. and rest of the thing is same inside as in equation 8. So, that means BTE be determinant j, because now dV will be replaced by determinant j d zeta, d eta and d xi, and this is the triple integral. Now the stiffness matrix, the stiffness elemental matrix is now triple integral. So, this triple integral can be solved using any numerical integration technique. Gauss technique is also, Gauss points are also used. So, 3D element usually do not use a rotational degree of freedom, right. So, in that situation one can come across. Now, the second situation comes, suppose if there is a distributed loading. So, the distributed loading has to be converted into nodal forces, as I told you. So, for an example, this is the case where capital A is the area R which the total distributed load P comes here. So, it has to be distributed over the nodes. So, it has been distributed there, you see the nodal forces. If you choose a 20 noded hexahedron element, so it is distributed there. So, at each node around P by if the P load has been there, distributed load, so it comes out to be P by 12 almost. The corner node has got P by 12 and the middle node has P by 3. So, then one can find out the stresses. So, stress as the sigma is equal to E epsilon, and that is in the matrix form can be written as capital E capital B D, and then one can also find out the principal stresses sigma 1, sigma 2 and sigma 3. One can also calculate the von Mises stress, which is defined as sigma y if it is. So, von Mises becomes 1 by root 2, as if you under root sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square. This is what the von Mises stress. Stresses are evaluated at selected points including node on each element. Averaging, that is around a node, for example, may be employed to smoothen the fields, right. So, this way one can proceed when it is even the case of distributed loading. There are many cases one would try, but let us see what are the different elements that we come across in 3-dimensional cases. For example, this figure shows the solid different solid element solids that we come across, because depending on the type of solid one has to choose a proper element. So, if you look at this figure where baseball bat kind of solid is there, and it is axisymmetric solid. Baseball bat is a axisymmetric solid, and one can produce it by solid of revolution. Similarly, on the right side there is a soft hollow shaft that is also axisymmetric, and it can be produced by solid of revolution method. So, for these cases, because it is axisymmetric, so one can use the cylindrical coordinate system, and therefore you require a mapping, that means mapping from xyz coordinate system to r theta z system. That is the only mapping required. So, it is shown here like this cylinder, and r theta and z has been shown direction. So, like this is another case where the a kind of column subjected to horizontal and vertical load, and varying column it is. So the radius from the bottom to top it is varying. So under that situation also it can be taken here, and for this case, because axisymmetric ring kind of situation, so when you choose r theta z, so you can take one small element of out of this to analyze. There is no need, because it is axisymmetric as I told, there is no need to solve all the element. You choose a small region, you define the theta for that, and what has been done here, the same has been done here. So theta, and that is how you have r u direction in this, and this is what has been. So the displacement field in this case, when you convert from the mapping from x y z to r theta z, so the displacement field will be u in terms of r z, and w would be w r z, and circumferential component, there is no circumferential component. So, and then strain one can define for this situation as that is epsilon r, which is deva u by deva r, and epsilon theta as u by r, and epsilon z as deva w by deva z, and the strain, the shear strain, then one can write as deva w by deva r plus deva u by deva z, where other component of the shear strain is 0. Then this has been shown in equation 21. So you can look here, the d theta, r, u, and the corresponding r d theta and r plus u d theta. So the stressors, that is sigma r, sigma theta, sigma z, and sigma and then the shear component, that is the tau n, is nothing but capital E by 1 plus nu, 1 minus twice nu, and that is the vector corresponding to strain, that is epsilon r, epsilon theta, and this has been shown in equation 21 here. So for the axisymmetric case, if you choose a 3 nodal element, ring element, so all around, so if you choose this, so one can specify the r and u like this. So these are the element, so 1 2 3 and 1 2 3 the variation. So this shows the 6 nodal element, which is, we call it as a ring element. On the other hand, there is a 4 nodal element, ring element also, so one can see. So if it is 3 nodal ring element, one can find out the corresponding stiffness matrix, so stiffness element stiffness matrix, and that has been shown here in equation 23 in terms of r theta z, and if you extend it, the same becomes, if it is a ring kind 3 nodal, then it becomes equation 24. That means k becomes 2 pi double integral, that is in first integral is minus 1 to 1, second is minus 1 to 1, bt e b r determinant j d zeta d eta. That is how the for 3 nodal ring element double integral. Please note here double integral comes because of the symmetry. There could be many applications of these kind of element, for especially for the axisymmetric, like this is one of the application where rotating flywheel we come across. So this case, rotating flywheel where the angular velocity is w and in radian per second, and z is the vertical direction and r is this theta. So body force is specified here, and then in terms of other things, cylinder subjected to internal pressure, on the other hand it is shown. Other element, the press fit cases has also been shown. One has to see there again the ring and sleeve is there in case of press fit. We have Belleville conical spring as well as so it runs like this slide. So one can solve also here. So this is a geometrically non-linear large deformation problem, and iteration method like other, that is the iteration method is approach needs to be employed for this, where the solid element of 3D problem that we come across, especially for elasticity theory, it looks like here the stress state. So if you take this one, this shows what's the solid elasticity theory problem. So this is Belleville conical spring problem, where we have a kind of arrangement. So one can see the pressure is from the top on the screen on this kind of spring. So this is a geometrically non-linear large deformation problem, and iteration method is generally needed for solving this kind of problem. While solving the 3D elasticity theory problem, and especially when we calculate the stress and strain state. So if you refer this figure where the 3-dimensional element having a volume element is shown. So and the corresponding displacement in XYZ direction, and the shear as well as normal stresses. So it is calculated as this one. So the stress has got again 6 stress vector has 6 component, and it can be written simply as sigma ij matrix. Strain likewise 6, and then the stress strain relation comes over here. So this stress strain relationship you can see the E matrix, which is the diagonal matrix, and all other matrix, the other components are 0 almost. So the stress is capital E epsilon, and displacement vector therefore one can write is as u xyz, v xyz, w xyz, and that is equal to ui u1, u2 and u3 vector. Strain displacement relation can also be likewise find out, like strain in x direction is deva u by deva x, y direction deva v by deva y, and z direction strain is deva w by deva z, and the shear component is also written, and this is what has been shown here in equation corresponding. Or simply the strain, shear strain can be written as 1/2 of deva ui by deva xj plus deva uj by deva xi for I and j to be 1, 2, 3. Or in a very simple manner, epsilon ij is half of uij plus uji, that is the tensor form equation. As I told you, for this situation then the equilibrium equation is also needed, and this shows the equilibrium equation. So that means for the 3-dimensional case, the equilibrium equation, when you ignore the body forces and all those, so if you have body forces Fx, traction forces rather Fx, Fy, Fz, so that becomes deva sigma x by deva x plus deva tau xy deva y plus deva tau yz deva z plus fx is equal to 0, and likewise the 3 set, that is sigma ij plus fi is equal to 0. These are the equilibrium equations in tensor form. And then you require the boundary conditions, that is the boundary conditions like on the specified displacement boundary, and boundary condition, that is the traction on the specified traction boundaries. So traction in fact becomes sigma ij nj. Nj is the normal direction. So one can see here the two reason. Then you can go ahead with the stress analysis. So solving these equations, earlier equation, especially equation corresponding to what that is 30 is your equilibrium equation, 31 is your boundary condition equations, and that means equation 28 to 31. If you, so these equations provide the stress, strain and displacement fields, right. So 15 equations for 15 unknown for any 3D problems one can have, and analytical solutions are in fact very difficult to find out. Then if you have these things, then one can go ahead with the finite element formulation. So wherein you have to find out the displacement field, that means the displacement u, w, u, v and w has to be represented in shape function, and this is what is shown here in that is u is summation I to n ni ui, and likewise. So in terms of nodal values, and then the same can be converted into matrix form, as you remember earlier also. So that is the UVW, that is the displacement vector has got, and the shape factor multiplied by your displacement. So u is n d. So using the relations one can then derive even the strain vector, that is equal to capital BD. So strain here it is 6 by 1 and capital B is 6 by 3n, and D is 3n by 1. So n, it depends on the number of elements. Then one can choose the stiffness matrix K, which is over the integral BTEB dV. So K for this case would be 3 by n, BT, that is your transpose of the B matrix, would be 3n by 6, E will be 6 by 6, B will be 6 by 3n. So numerical quadrature rules are very often required to evaluate the above integration, that is the stiffness matrix integration. In fact, the rigid body motions for 3D bodies, that has got 6 component, that means 3 translation and 3 rotations. So these rigid body motions causes for singularity of the system of equations, and therefore must be removed from the FEA node model to ensure the quality of the analysis. So this is what's the basic for the stress strain calculation and FEM formulation for 3D problems. One can also utilize, and it is often utilized in thermal analysis. Even in metal forming we come across the heat because when you solve the hot extrusion, hot forging, hot rolling cases, so we quite often come across. So the finite element can also be utilized for those situations, and there is a, in fact, the rigid plastic formulation or Galerkin, all those things, along with it is valid for stress strain, and you can also associate this with the thermal. If you have a material property that correlates stress, strain and temperature. So sorry, the stress which is the function of strain rate and temperature. So in that case you can use thermal analysis. So all kind of thermal analysis has two objectives. One, to determine the temperature field, either in the case of steady or unsteady case, and secondly the stresses due to the temperature changes, that is also very important. And therefore the stress equation earlier, whatever we have used, power law or whatsoever, which was earlier either defined in terms of the strain and strain rate, when temperature comes into picture, these stresses has to be defined and must be known for a particular material in terms of strain, strain rate and temperature to deal with hot forming processes. So let us start with the simple case, 1D case, where the temperature field, and then you know the Fourier heat conduction equation. So in simple 1D case, where it can be written as Fx is equal to minus k deva T by deva x. That is the what the simple equation number 1 for the temperature field, where Fx is the heat flux per unit area, K is your thermal conductivity, and capital T is your temperature function of x in terms of x. So if your element is this way, varying from this to this direction, so x is the direction shown. And in case of 3D case, we may have the Fourier's heat conduction equation, and therefore Fx, Fy and Fz will come, and it will be equal to simply capital K deva T by deva x, deva T by deva y and deva T by deva z, where Fx, Fy and Fz would become the heat flux in x, y and z direction respectively. And in that case the isotropy, when the isotropic is there, so capital K matrix would be written as simply 3 by 3 matrix, where the diagonal is k, k, k and all other elements are 0. This is what has been shown in equation number 3. So then you require the equation of heat flow, and this can be in the form of equation 4, that means minus deva Fx by deva x plus deva y by deva y deva Fz by deva z plus q v is equal to C rho deva T by deva T. Then that is shown in equation 4, where QV is the rate of internal heat generation per unit volume, C is your specific heat, and rho is your mass density. So for steady state case, where deva T by deva capital T is your temperature, and small t which is taken as time. So for steady state case, deva T by deva small t is 0, and for isotropic material one can then obtain K delta T is equal to minus Q, and where Poisson's, this is also called as equation number 5, is also called as a Poisson's equation, right. And then one can impose the boundary conditions, like if this is the situation, so you have the ST and Q, n is the normal to the given surface. If we take the 2D case here, so boundary condition can be imposed like T is T bar on ST surface and deva T by deva n is equal to capital Q bar on the SQ form surface. Please note that at any point on the boundary, that is boundary S, when it is S, is union of that is ST is with union of SQ, only one type of boundary condition can be specified, no any other boundary condition when it is in union. Then once these boundary conditions and the heat transfer flow equations and things are decided, then one can seek the finite element formulation for heat conduction. So simply the finite element formulation becomes Kt, capital T is equal to Q, where Kt is your conductivity matrix, just like your stiffness matrix earlier. So Kt becomes the conductivity matrix, T your vector of the nodal temperature and Q is the vector of the thermal loads applied from external cases, and then the element conductivity matrix is written as 8. So you can see the similarity with the stiffness matrix earlier. So the element conductivity matrix is given as Kt integral over the volume or the domain Bt K B dV. So this is obtained in a similar manner as for the structural analysis we did. That means by starting with the interpolation, that is T is equal to Nt, where n is the safe function matrix and T E is your nodal temperature. There is only one degree of freedom at each node to remember for the thermal problem. Okay. So the thermal transient analysis on the other hand can be represented as deva T by deva small t, which is not equal to 0. If it is steady state, it is equal to 0, but if it is transient, then deva T by small deva T is not equal to 0, and then one can apply the FDM, that is the time step, and integrate in the given time steps as in the transient structural analysis to obtain the transient temperature fields. So this is what the things are followed. Then the second part, as I told, the thermal stress analysis is also carried out, and this is what is important for us in metal forming as well. So solving the previous equation 7, one has to first to find the temperature field and then apply the temperature changes, that is delta T, as initial strain or the initial stresses to the structure. So let us take 1D case here, where the one element is a so the temperature at T1 is given, and this is at T1 there is a change in the temperature. So the thermal strain, that is the initial strain, is epsilon 0, which is alpha delta T, in which alpha is the coefficient of thermal expansion and delta T is T2 minus T1 is the change in temperature. So the total strain becomes epsilon, which is equal to epsilon 2 component. So the elastic strain due to the mechanical load and another due to thermal load. So the total strain, that makes the total strain, and therefore the epsilon becomes capital E inverse sigma plus alpha delta capital T, or simply the stress, that is the thermal stress, is E multiplied by epsilon minus epsilon elastic strain. So, this is what is shown here in 12. We can take certain problems to see the applicability of this thermal analysis. So, in the above problem, which was the bar under thermal load delta T, if no constant on the right hand side, that is the bar is free to expand after expansion temperature to the right hand side, that means the epsilon is equal to epsilon E and epsilon, the thermal is 0 and stress is 0. So, if you utilize equation number 12, so no thermal stress comes, first case, and second, if there is a constant on the right hand side, that is the bar cannot expand to the right hand side, in that case epsilon is 0, that means strain is 0, and therefore the thermal strain would be there. So, thermal strain can be calculated as minus alpha delta T, and therefore the stress, thermal stress can be capital E alpha delta T. So, from equation 10 and 12 one can find out thermal stress, and because it exists there. So, this was for the if let us take it for the 2D case, the thermal case. So, plane stress if it is taken as. So, the plane stress equation you have epsilon x, epsilon y and the shear strain. So, under thermal case epsilon x would be alpha delta T, epsilon y would be alpha delta T, and shear would be 0. On the other hand, plane strain case, because the Poisson ratio would come, so that would consist of the thermal strain as sigma x, sigma y and shear xy. So, that would be simply 1 plus nu alpha delta T, 1 plus nu alpha delta T and 0. So, where nu is your Poisson's ratio. The same thing can also be extended for the thermal case to the 3D cases. So, in that case simply there is a correlation with the static we did earlier. So, for the 3D case the strain, that is the thermal strain, would be have got 3 component, 6 component, 3 direct, sigma x, sigma y, epsilon x, epsilon y, epsilon z, and the shear strain 3. So, one can see the temperature change do not yield shear strain. So, total strain will be certainly equal to the elastic strain plus thermal strain, and then one can find out the stress strain relationship. As usual, the thermal stress analysis, when one utilizes finite element method, you need to specify alpha for the structure and delta T on the related elements which experience the temperature change. Secondly, note that for linear thermoelasticity, same temperature change will yield same stresses, even if the structure is at 2 different temperatures. And thirdly, the differences in the temperature during the manufacturing and working environment are the main cause of thermal residual stresses. So, this point one can note it down for when you apply it for the thermal stresses analysis using FEM. So, this has been taken as very brief, and one can practice many other problems for the thermal case. In fact, most of the metal forming problem comes into the large plasticity along with temperature, hot forming and all those things situation. There are many books one can refer. because earlier I could not mention you the books. You can follow Jinkovich and Taylor book, 1989 published by McGraw-Hill. You can also follow very popular book as J.N. Reddy, that is an introduction to the finite element method, that is 93 edition. There is another book called as R.D. Cook, then K.J. Bathe, and there are many. These lists I have mentioned here. So you can make use of these readings, these references for refreshing your deliveries what we have. Also I will suggest that you practice basics and then you go ahead with the simple 2D and 3D and then try for the thermal. But those 7 points of caution which I mentioned in lecture number 38, one has to always keep in mind. So hopefully now we have entered in the domain of 3-dimensional FEM. So next lecture, that is the last lecture, 40th lecture, which is supposed to the last lecture of this course, whole course, we would cover a case of 3-dimensional case of metal forming, especially metal forming, and we would see that whatever discussion we have done so far on the finite element method, how it is utilized. So we would meet in the last lecture 40th, and with the hope that you will be revising those things, and then we will meet again. So I thank you all for your patience, and please do not forget to give your feedback either through net or through email to me, and you can judge the qualities of this e-content course, which now we are at the verge of completion, through the net, so that your suggestions are included further for the other courses that we would be able to create for in future. So I thank you all once again. Thank you very much.